So next topic is about multitasking. In this set of slides, we're going to be focusing on threads, and we will talk about typical problems of thread programming and some possible solutions. Just give you quite a bit of examples to show how threads can help program concurrent functions, but also at the same time, how we as a programmer should be careful about the design of multi-threaded programs. There are different layers of abstractions for concurrency in programs. From the top, there are concurrent models of computation, data flow, time-triggered operations, synchronous operations, and underneath the processors supports interrupts, which are quite related to times. And also internally, it can be pipelining or multi-core to support different concurrent activities. In today's lecture, we're going to be looking at something in between to basically bridge the higher level abstractions models with the lower level processor functionalities. And this is where the multitasking fits in. There are different ways of doing multitasking: processes, threads, message passing, all related to multitasking. We're going to start with threads, and then we're going to later talk briefly about processes and message passing. Threads are essentially the key concurrent execution unit that we are going to talk about today. Threads are sequential procedures that share memory. So threads are oftentimes multiple, and these threads themselves are sequential procedures. You can think about them as instruction sequences being executed. They are not static. They are instructions that are currently being executed as a sequence. And these threads at runtime, they share memory. And when they share memory, that means they share variables, and the instructions in them, when they use these variables, read or write, they actually read or write the same variable. And that's where the complication originated. We can use threads to react to external events like interrupts. We can also do exceptional handling, and that means the software interrupts. We can create illusions of simultaneously running different programs and try to exploit parallelism in hardware, especially when you have a multi-core machine. And also they will help deal with real-time constraints so that some tasks are not blocking the other ones. When you have multiple threads, the scheduling of those threads or the orders of their execution is not always well-known, well-defined. There are different variables, different dynamics. Predicting the thread scheduling is a iffy proposition. If there's no operating system, multi-threading is achieved with interrupts. So interrupts could be coming externally or could be internal. So the timing of these threads or the execution order is determined by these events. For systems with operating systems like Linux, Windows, OS X, so Mac OS, they provide thread libraries, oftentimes pthreads or POSIX threads. And with these libraries, it makes the programming easier, but as a library, they provide no fixed guarantees about when threads will be executed. So when you start up these different threads, you cannot say for sure that thread A is going to be executed before B. These libraries do not guarantee that. For real-time operating systems, things are a little bit different. They have different ways of controlling when threads execute. They can use priorities. They can use preemption policies, which means that at certain times, one particular thread can preempt or take over the CPU from other threads. And also, you can program deadlines so the threads can be better scheduled in a static way. So real-time operating systems, they organize, manage these threads differently for real-time purpose, so that the threads can be precisely executed, completed, and get your job done. Processes are a bigger concept. Processes are collections of threads with their own memory, but not visible to other processes. So a process can have multiple threads, and all the threads are within the scope of this single process. And these threads will be able to share the variables within this process. But a process is isolated from another process. Segmentation faults are attempts to access memory not allocated to the process. So when you have a process, you are given certain resources, especially memory space. You can only access these memory space. If the process tries to access the memory space allocated within another process, then that will cause segmentation fault. Segmentation fault is common in the early days or even nowadays. If you use Windows before, if you write your own Windows application, if there's a segmentation fault of some sort, you will see that big warning box or some message box pop up that you are saying your process should be terminated because it's access an invalid address. On Linux and Mac OS, if you run a program that has errors in accessing unallocated space, the OS will report segmentation fault. And that's to make sure that we have this protection so no process can cross the boundary to access memory space allocated in another process. Communication between processes are possible, but they must occur through OS facilities like pipes or files. POSIX threads or PThreads. PThreads is a set of API application programming interface implemented by many operating systems, both real-time and not real-time. It's a library of C procedures. Before POSIX threads or PThreads, different OS has different implementation of thread libraries. So it's almost impossible to port one multi-threaded program from one OS to another OS. And with the introduction of PThreads, everybody's using PThread API. So it's much easier to port applications written in PThreads or using PThread library and port that application from Linux to Windows or from Windows to Mac OS. It's standard by IEEE in 1988 to unify the different variants. And it implemented most of the operating systems right now. Java is also a concurrent library that you can call, and they are using pthreads underneath and provide thread constructs as a part of the programming language. All right, let's look at this first multi-threaded C program. So we have a few lines, 20 lines of code. The first two lines are include C header files. stdio is basically the standard input and output. PThread is the .h is the header file for PThread library. And then we have two functions. One is the main function we'll introduce a bit later. Then from line 3 to line 9, this is the function that we will use to instantiate a thread, a PThread. Let's see what this function does. So it's print n. It returns null pointer, and it takes one argument, and that's a void pointer. It's a pointer points to a address that's not really typed. Within the function, we declare a local variable I, which is used as a loop iteration variable. I goes from 0 to 10, so we're going to repeat, and this for loop, this line will be repeated for 10 times. And in each loop iteration, we're going to print a message. It's called myID:, and we're going to print the integer number, and then with a new line. Where do we get an integer number? So we actually use the argument, the pointer that passed into this print function, print n function, and we typecast that pointer into an int pointer, so a pointer to an integer, and then we do another heuristic and to get the value of that integer. So if you just look at this print n function, you can say that, oh, I'm gonna print a message saying, my ID is this number. I'm gonna print this for 10 times. Quite simple. And once that's done, I'm gonna return null. So this function completes. And then from line 10 to line 20, we have the main function. In the main function, we use pthread_t. So that's the pthread type that's declared in the pthread.h. And we have two variables, thread ID1, thread ID2. And then we have a pointer called exit status. And we have two integers, x1 and x2. x1 is initialized as 1, x2 is initialized as 2. And then from line 14 to line 18, we have a few pthread API calls. The first two lines, line 14 and line 15, we call pthread create. Pthread create is the API that we use to create a pthread, a POSIX thread. And it takes a few arguments. First is the thread ID that will be returned. And then the second is a null pointer for this case. And the third one, the final one, these are related to the function that we want the thread to execute. And that's exactly the function we declared earlier. So print n is going to be the third argument, which is the function pointer. And the final argument is a pointer to the variable x1. In this case, the next line is pointer to the variable x2. So what this line does is it will create a pthread. This POSIX thread will execute this function print n. And when we create this pthread, we pass this variable, this argument x1, into this print n function. So essentially, you can see we are passing x1 as the arg here. So when we have a thread that's created for this line, by this line, we will have that thread execute this function using x1 as the input argument. So can you tell me what the first thread will do?
It will print 1 10 times.
So it will print my ID 1, because the input argument is x1, which has the value of 1, and you pass in the pointer, the address of this x1 variable, and here you use that as the address to an integer. You typecast, you get the value, so you will actually get the value, integer value 1. So this line will print as my ID column 1 and a new line. So you will see at 10 messages, 10 lines, my ID 1, my ID 1, my ID 1 for 10 times being printed. And line 15 is similar, but in this case, we create another thread. So this create a thread, first thread, and this pthread creates another thread, the second thread. But this time we're passing in the pointer to x2 as the input argument. So this second thread will print my ID 2, okay, because x2 has the value of 2. And this line, my ID 2, is supposed to be printed for 10 times. And then after that, we have a message printed out as part of the main program saying started threads. We have 2 threads started. And line 17 and 18 are 2 pthread APIs, pthread join, which really waits for the completion of this thread identified by thread ID 1. So that's really identifies the first thread. And similarly, the line 18 is trying to wait for the completion of the second thread. So with these 2 lines, line 17 and 18, this will ensure that before this main function completes, it waits for the 2 threads to complete. Okay, so it seems straightforward. In the main program, we created threads and we print messages and then we wait them to complete. Now my question is here, what will be the outcome? Specifically, what do you think you will see on the screen in terms of the messages? So we know one of the threads will print my ID 1 for 10 times, and the other thread, the second thread, will print my ID 2 for 10 times. But will you see exactly, so my ID 1 print 10 times, then my ID 2 for 10 times?
No, I think it'll be kind of randomized. Like you won't be able to predict how it kind of interweaves.
Why is that?
Because both the threads start and then the CPU kind of decides which one goes at different times, and it's kind of hard to predict.
Precisely, that's correct. So the pthread, this is a pthread API to create the thread. So this API call finishes immediately after it creates the thread. But the execution or the scheduling of this first thread is not necessarily before the execution or scheduling of the second thread. And even when they are executing, there's no obligation between these two to say, oh, let me print my ID 1 first for 10 times before you print my ID 2. There's no such coordination. So you should expect to see really a mixture of these messages printed on the screen. Okay, can you see my screen?
Yes.
Okay, so let me make this larger. Okay. All right, so I double checked the pthread create API. Excuse me. So I misspoken about the second argument. So this pthread create, first argument is the thread ID. This will be filled in when pthread create returns. The second argument is actually the thread attributes. It points to a attribute structure. If you put null, pthread create will use the default attribute. we'll see what kind of attributes. And the third argument, as you see here, this is a function pointer. And this function, as we saw for print n, has to be declared as a function that returns a void pointer and then takes one argument, void pointer. Okay, and the last argument of this pthread create is the void type pointer, and that's going to be passed into this routine. So this is the pthread create API. So for the attributes, it's a structure that's going to be created using pthread attribute init or pthread attribute destroy. You don't have to use, or get so much detail about this attribute, but I'm just going to quickly show you what kind of attributes we're talking about. For example, how we should create the pthread, whether it's joinable or not joinable, the inherent scheduler or scheduling policy, priority, the stack size, etc. So most of the time you won't need to change any of these attributes. You can use the default ones, but if you want to go into fine-tune these different attributes, you can do that by creating an attribute structure and pass that structure into this pthread create when you call this API. Okay, hope that answered the question.
You have another quick question?
Sure.
So can you only pass in one argument? Like what if you wanted to pass in like a couple of arguments into
Very
that
good question.
start routine?
Yeah, you can only pass in one argument. However, because this is the pointer, you can then create a structure and then pass the pointer to that structure.
Oh, gotcha.
Yep. Okay.
Thank you. That answers
Welcome.
it.
Okay. So gonna back to the other. Can you see the slides?
Yes.
Yeah,
Yeah.
I can see it.
Okay. So we saw the very basic example from last slide. This is another example quite similar. So we have a function called thread function. It returns a void pointer and takes one argument. And this thread function returns something, or returns a pointer to something or a noun. In the main function, we have one thread to create. So we use pthread create, takes the thread ID as the first argument, use the default attribute, and use this thread function as the starting function, and then pass in the value here. So value is a integer, and we assign to something like a constant number 2, 4. So this is how I call this pthread create. Then after some time, we finish a few things. Then at the end, before the main function returns, I call pthread join to make sure this thread completes, and then before I close out everything. Okay, so we want to use this example to talk about a few things. First, when we use pthread create to create a thread, even when this API itself returns, so we finish this line, we move on to the next line, that doesn't mean that the new thread has started. It may or may not start running. So it really depends on the thread scheduler. If you have multiple ones, that's even more significant in the sense that you don't really know which thread is going to be executed first or second. There's no guarantee how these threads are going to be started in certain order. So you may have a lot of non-deterministic cases, scenarios. Second thing is about the input arguments to the thread function. We know that we can pass in a pointer, and this points to a void type. So this value here, it's if you look at this value, this variable, it's a local variable to the main function, right? If you remember last time, we talked about static variable, local variables. Local variables, excuse me, local variables are allocated on the stack of a function, and that space will be deallocated, will be released when the function returns. So in this case, we use value, which is a local variable of the main function, and we pass in that the pointer to that variable. Now, the question here is this okay? If it is okay, and why? Why here this local variable can be used, its address can be used as the input argument to pass into the thread function. I hope you understand my question. So normally we say the local variables of a function will be released, deallocated when the function returns. So it's not always safe to use the address to this variable or even the variable itself if you are going outside the function. But here we use the address of this value, this variable, as the input argument. Is that okay? If it is, why?
Yeah, I think it's okay.
The reason?
Because pthread join ensures that we don't return out of the function before completing the thread function method, which passes in value.
Very good. Yeah, exactly. We know main function is the kind of the entry point of your program. So this function will execute. This function will return only when it gets to this point. But before it gets to this point, it has to finish this pthread join, which will wait for the completion of the thread function. So during this time, the value, this variable is still allocated, so its address can be safely used. Now, the next thing is when you return from the thread function, this pointer to something. If we say we have here a integer x equals to 5, okay, if we declare integer x equals 5 and we do some operation on the variable x, and then we return the pointer to that variable x, is that okay?
Professor, that should be okay because it's returning a void pointer. That means it can point to anything, integer or character.
Okay, so that's one idea. And any other points, different thoughts? Now think about this. So if we have an integer x equals to 5, this integer, this variable x, where is it allocated? In the static memory or in the stack?
On the stack?
Stack.
So it's on a stack. So, and this variable is a local variable that is allocated on the stack. And so when this function returns, that variable, the space allocated to that variable will be released. If you return the pointer to that variable, that means this pointer will now point to a memory location that's not allocated, that's just being released because this thread function returns. And if you use that pointer somewhere in the main program or anywhere, then that's a problem because you're trying to access a location where the space has already been released. So it's now invalid. So you should not return a pointer to a local variable. I hope that's clear. Any questions? Okay. Yeah, here, because the thread join returns only after all the threads have terminated. Okay, so this is the kind of the example I was talking earlier. So we have one thread function that I want to use. It's called myThread, and it declares local variable in a return, assign the value of 42, and then I return the pointer to this variable. Okay, and we have in the main function the pthread ID, TID, status, and then we call pthread create, use the default attributes, and use the myThread function, passing no arguments, and thread join, wait for the thread to complete, and once it completes, we'll print the return. So can we see this 42 printed out?
No.
What do you expect to see?
Well, it could be anything, since by the time you return the function, return that pointer, or you're trying to return the address of a local variable in myThread. So I'm not too sure.
Right. So I think you're really on the right track. This is exactly the things we talked about earlier. You should not return a pointer to a local variable, which is on a stack. And when this function returns, this variable, the space allocated to this variable is gone. And you should not access that using the address. So I don't think it will print anything. In fact, it should report a segmentation fault. Okay, so several notes about when you use threads, and especially pthread libraries. The reason you want to use thread is that they share memory spaces, and that's sometimes good, and well, most of the time good, because we do want these threads to work collaboratively using shared variables. Also, in terms of thread scheduling, they may or may not be running immediately after being created. Also, a thread may be suspended between any two atomic instructions, and you have no clear control about when they will be suspended. It's all influenced by the thread schedulers. And the scheduler can choose to execute another thread, or in the case of interrupts, it will execute interrupt service routine. You can assign priorities using the thread attributes, but depends on the thread scheduler you use, the priorities may not take effect. So you use a combination of setting the priorities and also choose the thread scheduler if you want to enforce certain kind of scheduling policy. And a big part of the programming practice using thread is that you will use the help of mutexes and semaphores. And we'll talk a lot more about those in the later part of this lecture.